Okay, good morning. Let's wrap up chapter 6 today. So let's see. Start recording. Perfect. Does this remind you of? Yeah, just one student. You're college students. If this is not familiar to you, you need to like get out more on Friday and Saturday nights. Nah, I'm just kidding. I know you're all under a lot of stress. But yes, this is a loudspeaker. Anyone know what this is called? So the loudspeaker has like 3 individual speakers in it. Okay, so this is technically a loudspeaker box that has 3 individual speakers in it. But in generic terms, we call it a speaker, and then we say that the individual speakers are drivers. So speaker drivers. So how about the small one? Anyone know what this is called? Made famous by Twitter, but it's known as a tweeter. The large one is known as a woofer. And this one is for mid-range for vocals. Are these words at all familiar? No? Never heard of woofers and tweeters? Loudspeaker box has 3 individual speaker drivers, different sizes. There is a specific purpose. Depending on the incoming frequency that it reproduces, all right, let me back up. Depending on the value of the incoming frequency, it is directed to each one of these speaker drivers because each one of them has a specific function in reproducing the sound waves. Low frequency signals require a larger surface area because of their wavelengths. And so a woofer reproduces the low frequency range. Okay. The lower the frequency, the larger the speaker size. Okay. Tweeter, the small ones, reproduce the higher frequencies. Okay, low frequencies are the loud thumping noises, the bass sounds that you hear. Tweeters, the high frequencies, which are the treble sounds. Okay, and mid-range are for vocals in general. And there's also a certain overlap between all 3. If you look at the back of any kind of loudspeaker box, you only have 2 connections, a plus and a minus. Professional loudspeaker box like this, like a 3-way loudspeaker, will have 2 banana jacks in the back. Basically 1 cable that's going in, right? Every cable is a plus and a minus. It's only 1 cable that's going into this box. But if you open this up, if you open it up, and it doesn't take a lot, there's only 2 screws on the back. Take those 2 screws out, you can remove it. And from the opening in the loudspeaker box, you will see that the internal connection goes into a much larger circuit. And depending on the make and model of your speaker, the large circuit may have a few inductors, heavy coils, a few capacitors, and a few resistors. This circuit is known as a crossover network. Crossover network. and you will see that it splits the output in three. Splits the output in three, each one of them going into each one of those speaker drivers. And the technical name for this crossover network is an electronic filter, electronic bandpass filter. Low pass, high pass, and bandpass. Okay, bandpass. Crossover network is a band pass filter, a high pass filter, and a low pass. Okay. Electronic filters can be very cheap to make. If you just use R and C, you can make a high pass RC filter, you can make a low pass RC filter. You combine all together, you can have like a band pass filter using only 2 resistors and 2 capacitors. Wouldn't even cost more than 25 cents. So cheap speakers, cheaper ones, I literally have seen where the filter is not a circuit at all. It's not like there is no circuit board, there are no wires. You simply have resistors and capacitors that are directly mounted on top of the speaker drivers, like no circuit required. So the cheapest speakers, like the small cube speakers, you can pick up for like 10, 20 bucks. We literally have simply a resistor and a capacitor. Less than 20, 25 cents to make those kind of filters. Slightly higher quality ones, like the ones in this room, I'm assuming they probably cost a whole lot more because they're professional speakers. So they would have an actual circuit board with higher quality components. Okay. And the really expensive ones will probably have something like an inductor, a capacitor, and a resistor, okay, to do high quality filtering. So what it does is it combines both a low pass and a high pass filter in one. So let's say you have a characteristic that looks like this. Frequency versus output voltage, and you have turn out quite right. Okay. This is the frequency response of a low pass filter. This on the top and the right is the frequency response of a high pass filter. Right? You guys agree? High pass and low pass. 2 separate independent filters. Now, if I take the cutoff frequencies of both, this is the cutoff frequency for the low pass filter, and this is the cutoff frequency for the high pass filter. If you design a circuit that comprises of both filters in one, depending on the values of the components, you have 2 cutoff frequencies, right? One for high pass, one for low pass. There is a band of frequencies in the middle that is allowed to pass through. Everything outside of this band is blocked by both filters working in tandem. Okay, so a band pass filter is a combination of a low pass and a high pass filter working together. Make sense? Right? You have 2 cutoff frequencies, and those 2 cutoff frequencies are positioned with some distance away from each other. There's a certain band of frequencies in the middle that is allowed to pass through, and you obtain a band pass filter. All right, any questions so far? So if I take a circuit, let's say inductor L, resistor R, capacitor C, if you ignore the inductor and you have simply an RC circuit, RC filter, if you take the output across the capacitor, what would we obtain? That's the first filter we studied. You obtain low pass filtering. If you take a RL filter or RL circuit and you take the output across the inductor, you obtain a high pass filtering action. And depending on, again, the values of FP, you get a certain band of frequencies that are allowed to pass through is if you take the output across the resistor, okay, RLC. So the exact same circuit, you can have 3 filtering actions depending on where you take the output. And each one of those 3 would go, one of them would go to a tweeter, one of them to a mid-range, another one would go to your woofer. And then frequencies below the woofer are reproduced by a specialized device known as a subwoofer. The lower you go in frequencies, the more power you need. So if you actually want good sound reproduction, you need an amplifier which can supply a whole lot of power. Okay, so 2 frequencies, 2 filters in one circuit, band of frequencies allowed to pass through the middle. If you have an inductor and a capacitor in the same circuit, you can have an RLC components. RLC would give you a band pass filter. Now, when you have RLC, all 3 of them in one circuit, you have 2 energy storage devices, but both of them work the opposite. Inductor, in a positive half cycle, when you apply an AC signal, the energy flows into an inductor in the positive half cycle, and in the negative half cycle, it's reversed and the energy flows out. Capacitor is the opposite. Capacitor, energy flows in the positive, energy flows into a capacitor in the negative half cycle and flows out in the positive half cycle. So if you have an inductor and a capacitor in the same circuit, positive half cycle, energy flows into the inductor, negative half cycle, energy flows out, but it goes into the capacitor. Next positive half cycle, the energy flows out, goes into the inductor. So it bounces back and forth between the inductor and the capacitor. When a switch is first flipped on, both of them are empty. Both of them are empty. There's no energy in either one of them. Positive half cycle, the inductor fills up. Negative half cycle, the capacitor fills up. From that point on, the energy is localized, bounces back and forth between the two like a ping pong ball or a tennis ball. Okay, this is a very important concept which we will use again, or we'll come across again in chapter 7, AC power, and lab 8. When you have an inductor and capacitor in the exact same circuit, the energy bounces back and forth between the two. Okay, so if your source is supplying 10 volts of energy, combined with the stored energy in there, you might obtain voltages and currents that are larger than the source. That's the reason why, because of the stored energy in the circuit. Okay, if the inductor and the capacitor do not discharge fully, which would never happen if it's like an RLC circuit, then you'd have voltages and currents that are much larger. Now, you have a range of frequencies being applied to an RLC circuit. At one particular frequency to this RLC circuit, the impedance of the inductor and the capacitor cancel each other out. At one particular frequency, what happens is the impedance of the inductor and capacitor have the exact same magnitude. Magnitude of ZL will be exactly the same as the magnitude of ZC. But the phase would be exactly opposite. Inductor is plus 90, capacitor is minus 90. If they share the same current, it's 180 degrees out of phase. Remember at the beginning of chapter 1, I plotted something like this. Not plotted, but I showed you something like this. If you have a signal and you add it to the exact same signal, but 180 degrees out of phase, what do you get? 0. Real life application? Anyone remember? Noise cancellation. You take an incoming signal, invert the phase by 180, add it to the same original signal, output goes to 0. Same concept. Magnitude of ZL and magnitude of ZC are exactly the same at resonant frequency. That frequency is known as the resonant frequency and noted as F0. F0. But the phase is exactly the opposite. So the cumulative effect of ZL and ZC connected in series is 0. Hence, your total ZEQ as seen by the source, which should be R plus ZL plus ZC in a series circuit, is effectively only R, because ZL and ZC in series goes to 0. So the only impedance left in the circuit is purely resistive R. That's it. And the output goes maximum. Okay, again, at one particular frequency known as the resonant frequency F0, the impedance of the capacitor and the inductor add up to 0. And because they add up to 0, the only impedance left in the circuit is the pure resistor R, and the output goes to max. For all other frequencies lower than F0 and higher than F0, the output is much lower. And so you obtain a curve that looks like a bell. Represents the frequency characteristic of a band pass filter. The output is at a maximum right at the center at F0. Okay, at F0. And F0 depends on the value of the components L and C. So F0 is 1 over 2 pi root of LC. 1 over 2 pi root of LC. If we connect all three components in series, RLC, we get a series resonant circuit. When you connect it in parallel, you get a parallel resonant circuit. The effect is still the same. At resonant frequency, ZL and ZC combine, but because they're connected in parallel, it goes to infinity. And the only thing left in the circuit is the pure resistor R. So for a parallel resonant circuit also, output is at a max at resonant frequency F0, and the equation is, again, the same. F0 is 1 over 2 pi root of LC. The equations for both series and parallel resonant circuits are exactly the same, except for one quantity, Q. So I'll talk about that in just a little bit. Let's take a pause. Let me know if you have any questions. So the question being asked is magnitude of VR, Vs? Yes, because output is being taken across the resistor. For a parallel circuit, of course, everything is in parallel. So VR is VC is equal to VL. Everything is the same. But in a series resonant circuit, output taken across the resistor, VR, is where you'd obtain the band pass filtering. Hence, the y-axis tells you magnitude of VR over the source. Essentially, it's just showing you the transfer function, output voltage to input voltage, Vs. Okay. Any other questions? Here, I pointed out that the first frequency on the left, the lower, okay, sorry, go ahead. I was going to explain it later, but let me explain it now because the question came up. So how does it go to infinity in parallel? Well, in parallel circuits, ZEQ would be the reciprocal of the sum of the reciprocals. So 1 over ZL plus 1 over ZC, and then the reciprocal. So if we take just the inductor and the capacitor, we have, what do we have? ZL times ZC, ZL plus ZC. And we flip those. So we are only looking at the parallel combination of the inductor and the capacitor. That's all we are looking at right now. And we get ZL times ZC divided by ZL plus ZC, which of course, at resonant frequency, this goes to 0. So at resonant frequency, this ZL and ZC combination effectively has infinite impedance. Because it has infinite impedance, nothing goes down the inductor and capacitor combination. Everything goes through the resistor. Make sense? Any questions? Okay, so I was pointing out that here the lower frequency FB for the high pass filter is noting the FB for the high pass filter, and the higher frequency is noting the break frequency FB for the low pass filter. So they are termed FH and FL, but the L and H have no meaning beyond the actual values. Okay, so it's just one thing I wanted to point out. The L and H subscripts have no meaning beyond the actual value. Right? You start from 0 on the left and increasing values as you move towards the right. FH has a higher value than FL. That's all it means. But in reality, the FH is referring to the low pass filter. FL refers to the high pass filtering option. The difference between the two, as I said, is the band of frequencies that is allowed to pass through. And so we describe that term as the bandwidth of this filter. Okay. In qualitative terms, if you have a band pass filter, you want the band to be as narrow as possible. So in terms of the resonant frequency, we can say it's the ratio of the resonant frequency to the bandwidth. Okay. The smaller the bandwidth, the higher the quality. And the larger the bandwidth, the lower the quality. But again, depends on your application. Most filters that we use in real life are bandpass filters. But ideally speaking, you only want one frequency to pass through. As example, if you set the FM radio station to 101.7 megahertz, you're tuning your radio station to only allow that particular frequency to come in. Everything else should be blocked out. But in real life, you can never have a filter that will only allow one frequency to pass through. It'll always be a narrow band of frequencies around that single frequency. So if it's 101.7 megahertz, if somebody broadcasts at, let's say, 101.7, so if somebody broadcasting at 101.76 perhaps, some of that signal might filter through, might come in. Have you ever had two radio stations coming in at the same time? Anyone? If you tune your radio station, if you tune your radio device between two radio stations, you're setting the filter right in the middle of those two bands. And so it might filter out a little bit of one station, filter out a little bit of another station, but both stations will have some signals coming through and you'd hear two radio stations at the same time. And what is happening is you're tuning the filter to be in the center between two bands. Yes. Kind of, yeah. Question being asked is about, is it low and high of others? But that low and high technically just refers to the filtering action. Doesn't, in real life, doesn't really matter. Yeah. Low and high would be relative, right? If it's 100 hertz break frequency, 200 hertz would be high frequency. But if it's a 1000 hertz filter, then 200 is low. So it's just relative. Okay, so that's bandwidth. And then QS, of course, the S stands for series and P stands for parallel. So it's the same equation, but in terms of the value, in terms of the components, the equations are reciprocals of each other. So QP in terms of RL and C is given here. And for QS, it's the exact opposite. It's the reciprocal of the exact same equation. Of course, you don't have to memorize any of these equations. Okay. If the quality of this filter circuit is larger, let's say if Q is much, much larger than, let's say, 5 or 6 or 10, then the curve may be symmetrical around the resonant frequency. And if it's symmetrical, then we can state that F0 is probably halfway between the two frequencies. Okay, it's halfway between the two frequencies. But that's not always the case. If you're doing lab 7 this week, then the band is very wide. It's not asymmetrical. It's not a symmetrical curve. You'll get a bell jar, but it's not symmetrical. It's very wide. Okay. So those are the resonant circuits. Let's take a pause. Let me know if you have any questions. Yeah. Quality. This quality is different from the quality of the inductor or a capacitor. Okay, this is the quality of the circuit as a whole. This is the quality of the circuit to function as a filter. Okay, the circuit, we are only looking at the filtering. We are only looking at the filtering function of this resonant circuit. So QS or QP is simply describing how well the circuit would work as an electronic filter. That's all it means. Yes. Mm-hmm. Yes. Um, I mean, the magnitudes and the phase, no, it's different. Yeah. Any other questions? Okay, so then let's talk about the last topic, which is Bode plots. Parallel resonance. Bode plots, as we spoke about previously, is a plot of the transfer function as a function of the frequency, right? Output versus input frequency. How is it changing? So the little bit of background is when telephone engineers were first installing telephone lines, they wanted to quantify the performance. And so tried to plot a very large range of frequency values onto a single chart was a problem. So they had to find a way to compress the axes of this frequency response. You had frequency response on the, you had frequency on the x-axis, and you had the output voltage of the transfer function on the y-axis. And so because we are working with a very large range of frequencies, they had to find a way to compress all of that data onto one single chart. So H.W. Bode, an engineer working for Bell Labs, came up with Bode plots, where you could actually take a large range of frequencies, compress them, and plot it as straight line approximations. Okay. And then again, they were very handy to actually manually plot out the frequency response. So let's see how we can do that. Introduce the concept of decades and octaves. So frequency is plotted on the x-axis. If you want to compress these data points, we use the log scale. And the way we do it is by plotting each frequency as part of a decade. Okay. So what is a decade? If you take the ratio of any two frequencies and you take the log of those frequencies of that ratio to the base 10, is known as 1 decade. If you take the log of the ratio to the base 2, it is known as 1 octave. Basically, if the ratio of the change of two frequencies is 1:10, it is 1 decade of frequencies. If you go from 1 hertz to 10 hertz, it's a change ratio of 1:10. So 1 hertz to 10 hertz is a decade of frequencies, 1 decade of frequencies. If you go from 10 hertz to 100 hertz, the ratio of change is still 1:10. Hence, 10 hertz to 100 hertz is also a decade of frequencies. If you go from 10 hertz to 10,000 hertz, you are going from 10 hertz to 100 to 1,000 to 10,000. So the ratio of change from 10 hertz to 10,000 is 3 times. 1:10, 1:10, 1:10. Make sense? So it's 3 decades of frequency change. An octave is a 2:1 change, twice. So if you go from 50 hertz to 100 hertz or 25 to 50, the ratio of change is 2. So that is 1 octave of frequencies. We are only interested in the decade of frequencies. Okay. So the x-axis is plotted using the log scale. So you're compressing a very large value of frequencies into a small area. And then they came up with a new unit to quantify the power loss. So think about this. Telephone lines, first being installed over 100 years ago, sending in power at the telephone exchange, you obtain power out at the consumer's residence or office. There is a lot of loss occurring in the transmission lines. How do you quantify that loss? A very large value to a very small value. Well, again, they figured out a way, and the FA is basically, again, the same thing. Take the ratio, take the log, but they came up with a new unit known as bells. So base 10 log of the ratio of two powers, P2 to P1, gives you 1 bell. Named after make it even more smaller unit, took 10 parts. Remember unit prefix table from chapter 1. Deci, centi, milli. Deci is 1/10. Centi is 1/100. Milli is 1/1000. So you have a unit known as decibels, or more commonly known as dBs. dB. So 1 dB is 10 times log of P2 to P1. Power is V squared over R. When you plug in V squared into this equation, 10 log becomes 10 times 2, right? Log of V squared. And hence you obtain 20 times log of V2 over V1, which is where our transfer function comes into the picture. Transfer function is a ratio of two voltages, V out to V in. Hence, if you wish to if you wish to express the magnitude of our transfer function in dB, in decibels, the equation is 20 times log of the magnitude of H of F. So your data points for H of F, input voltage and output voltage, is now compressed. Let's take a pause. Let me know if you have any questions. Okay. All right. And then we obtain a chart that looks like, well, not obtain. We plot it on a chart that looks like this. How many of you have used this kind of chart before? So as engineers in your own field, you may have used this some of you may have used this in the past. If not, at some point in time, you may use it as engineers. Okay. Most of the charts that you're familiar with, plotted on the linear scale. Linear scale is a summation. A log scale is a multiplication. So linear scale, we add 1 plus 1 plus 1 plus 1 plus 1. So we can begin at 0 and add 1. So 0 plus 1 plus 2, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then again, plus 1, plus 2, plus 3. So linear is a summation. Log scale is a multiplication. Log scale is a multiplication. Every division here has a multiplier. So every large division has a multiplier. The multiplier is the exponent. Depending on your needs or your application, you can begin at 10 raised to 0, or you can begin at any exponent value you wish. So let's begin at 10 raised to 0, 10 raised to 1, 10 raised to 2, 10 raised to 3, and 10 raised to 4. Okay. And because this is a log scale, there is no 0. Straight up 9 divisions. 1, 2, 3, 4, 5, 6, 7, 8, 9. That comprises the entire distance between the two multipliers. Okay. So instance, if I was starting at 10 raised to 0, my first division is 1. I would plot it as 1 times multiplied with 10 raised to 0. So 1 hertz. Second division would be 2 times 10 raised to 0. So 2 hertz. 3, 4, 5, 6, 7, 8, 9. After 9, it changes into a new multiplier. So 10 raised to 1. So it again begins at 1, but this time it's 1 times 10 raised to 1 gives me 10 hertz. Then it's 2 into 10 raised to 1, 3 into 10 raised to 1. So 10, 20, 30, 40, 50, 60, 70, 80, 90. After 90, again, a new division, a new multiplier, 10 raised to 2. So I get 100, 200, 300, 400, 500, so on and so forth until we get 1,000, 2,000, 3,000, all the way up to 10,000. And then 20, 30, 40, 50, 60, 70, 80, 90,000 until we get to 100,000. Does that make sense? 100,000 data points all on a standard letter size paper. If you were to plot it on a linear scale, you would probably need paper that's miles long. I'm just guessing. Right? So you take a large range of data, you compress it, and you plot it all in that same, sorry, not compress it. You take a large variation of data going from 1 hertz to 100,000 hertz, and you can plot it on a compressed scale, hence the log scale. Y-axis for a Bode plot, we plot as decibels. Whether it's voltage or magnitude of the transfer function, you are compressing the data itself. Okay, the data itself is compressed before we plot it on the y-axis or before we plot it on the chart. Hence, the y-axis is linear. Okay, big difference. The frequencies are not compressed, but the axes, the y-axis is compressed. Log scale. But when you're plotting the data points, the magnitude of the transfer function in dB, we are already taking the log, so we're already compressing the data points. So we don't need to compress the y-axis. The y-axis is linear because the data points themselves are compressed. Okay. And hence, this chart or this graph is known as a semi-log chart or a semi-log graph because only one of the two axes is in log. The other one is in linear. If both axes, both the y and the x-axis are in the log scale, you would have a log-log graph or a log-log chart. This is a semi-log graph. When I was a student, we used to buy this from a store. You could buy these charts and you just call them like semi-log graph paper. Like how you have engineering paper that has linear axes on both sides. You can buy these. Nowadays, of course, you can simply download it and just print it out. Okay. So that's essentially how a semi-log graph would work. All right, any questions? And that is how we actually make Bode plots. Okay, so there is one more thing I wanted to cover. And this came up in response to a student question. So the question they asked me was, how do we obtain the magnitudes and the phase? So I'll cover this. It actually leads into two different explanations. The transfer function, and I will do this for the low pass filter, but it's the same for the high pass also. Transfer function of a low pass filter is 1 over J F over FB. Okay. If I wish to find the magnitude of a complex number is, or we could plot it as the two sides of a right angle triangle. The magnitude of the right angle triangle, the magnitude of this complex number is the hypotenuse of the right angle triangle. So the magnitude of A plus JB is A square plus B square. And the phase is given by tan inverse of B over A, right? The two sides of a right angle triangle. So if I wish to find the magnitude of the transfer function, and write it as the magnitude of the numerator divided by the magnitude of the denominator. The denominator I can write as root of 1 square plus F over FB. That's where it comes from. Make sense? That's how we get this equation. 1 over root of 1 plus F over FB square. And then the phase of H of F would be the phase of the numerator, which is just 0 degrees. It's just 1 in the numerator, so the phase is 0, right? The denominator, you're trying to find the phase for 1 plus j f over fb. So just the denominator would give you tan inverse of b, which is f over fb in this case, divided by 1. Make sense? And when you plug it back into the equation, what do you get? It becomes 0 minus tan inverse of f over fb. Hence, minus tan inverse f over fb. You can do the same thing with the high pass filter, but the high pass filter has a numerator term, jf over fb. And so when you find the magnitude of the transfer function, you have an additional term in the numerator, f over fb, right? It'll be square root of f over fb square, which gives you f over fb in the numerator. When you do the phase angle substitution, you would have tan inverse of b over a. It'd be tan inverse of infinity, which would be 90, right angle triangle. Tan inverse of 90, which would never meet up, right? Tan inverse of infinity is 90. So you get 90 in the numerator, and you have tan inverse of f over fb in the denominator. When you perform that operation, you get 90 minus tan inverse of f over fb. Does that make sense? Think over that. Let me know if you have any questions. And there's one more thing. What happens when the input frequency is equal to the break frequency? What is the value? Mm-hmm. 1 over root 2, which is where we get that 0.707 value. That's where it comes from. If you plug in power in here, power P is V square over R. So 1 over root 2 square gives you 1/2, 1 over 2. Hence voltage, at break frequency, voltage drops to 70%, but the power drops to 50%. There is an explanation and derivation for everything we do. It's just we don't have enough time in a quarter to actually go into everything. So this was a specific question that the student asked me to address in class, and so I addressed it for all 3 classes. But again, if you have any kind of questions for anything, please send me an email, see me outside of class. I'd be more than happy to explain. Okay, there's just not enough time to go over everything. So we'll end class here today, and we'll begin chapter 7 or chapter 5.5 in our book, AC Power, on Friday.